This is the first video of Module 2 on nomenclature and related concepts. This has a lot of new material. Module 3 will have a lot more new material, and so things are going to accelerate as we go along. So it's important to stay on top of things. We continue to use everything we've learned all along, so nothing's ever left behind. So nomenclature is the naming of organic compounds. Each organic compound ought to have a different name that describes its structure. So you should be able to describe or derive the structure from the name of a compound. A little bit of review from where we left off. Ethane, here's the molecule ethane. We see the structure. Remember, it's sp3 hybridized, tetrahedral geometry. We call it fully saturated, and when we say saturated, we mean fully saturated with hydrogens, meaning it has its full complement of hydrogen atoms for each carbon. All single bonds, all sigma bonds. We can write the molecular formula C2H6. We can draw it in shorthand a little bit like that. And you see the 3D version. So we've already gone through all of that. We're going to talk about linear alkanes or alkanes as a class of compounds. These are the simplest kinds of compounds. In fact, they are often purified from oil refining processes. There's a logical progression to the naming of alkanes. If they have two carbons, we use the prefix eth and the suffix ane for all the alkanes. So a two-carbon compound is like this, is called ethane. Here's a line drawing of it. Really, ethane is just a single line where implied carbons are on each end, as you see right there and there. So as we keep going, we just add one more carbon to the chain. So we're going to stay in a linear chain, 3 carbons. We have the prefix prop for 3, so propane, another fuel gas that's used to heat homes and do all kinds of things like that. Implied carbons on the ends and in the middle. So it's a 3-carbon linear alkane. 4 carbons, butane, like in a butane lighter. Pentane, hexane, heptane, octane, nonane, decane. It actually keeps going after 10, but we can stop at 10 because you pretty much get the idea at this point. They remain all in linear chains with these simple names. So if you just say heptane, typically you mean a linear chain, 7-carbon molecule, alkane, linear alkane. Numbering is a big part of nomenclature. So, for example, the molecule propane would be numbered from one end to the other, simply 1, 2, 3. We're numbering the carbons. Most organic molecules are on a framework of carbon atoms, so it's the carbon skeleton, so to speak, of the molecule that gets numbered in some kind of typical order. Butane would be numbered from one end to the next as well. So this is pretty straightforward so far. It does get more complicated. Keep in mind our goal with nomenclature will be to be able to write a name for a compound that fully describes that compound and does not describe a different compound. The name should be unambiguous, in other words, no ambiguity. Likewise, we should be able to draw a structure from the name or describe the structure with a name, so going back and forth. We can't really go any further without discussing the concept of isomers. Constitutional isomers is the first such topic. The definition of an isomer is that it's a compound that has the same molecular formula but is a different molecule. So what I have drawn here below are two isomers of butane. How do I know it's butane? Because it has 4 carbons. Implied carbons, 1, 2, 3, 4, as you see. Implied carbons, 1, 2, 3, 4. It's really important to recognize that those are where the carbons are. So clearly these are both butanes having 4 carbons. One is the linear butane, one is an isomer of butane, and we need to have a different name for these two molecules because they're different molecules. To make butane out of this molecule here, and we're going to call this normal or N-butane. To make N-butane out of this molecule here, what do you have to do? You should build the model to convince yourself of this. You actually have to detach a bond, for example, that one, move it over to a different position and reattach it. Anytime you have to detach and reattach bonds to make a different molecule, you definitely have an isomer, a different molecule. So, simply put, this molecule is commonly known as isobutane. Easy enough. Well, it gets more complicated, that's for sure. And the next step of this process, we're going to do a lot more work with isomers. We're going to get a lot more practice with drawing as many different versions of simple molecules as we can and convincing ourselves that those are isomers. So you're going to see a lot of those in your on your own homework problems. Now, alkanes lead to alkyl groups. So imagine a straight chain molecule, for example, like the ones we saw above, with branching alkyl groups. Alkanes branching off of them as substituent groups. So there's another new term, substituents. Something that's sort of tacked on, added on to the molecule in various positions. This is in figure 3.3 of McMurray. So the first one we show here is an alkyl group, and this squiggly line right here indicates that it's connected to some other group. So there's no implied carbon here. In other words, this is like the molecule methane, but instead, since it's a substituent group, we call it a methyl group. So substituent groups, when they're alkyl groups like these, have the suffix YL. So instead of methane, it's a methyl group. Instead of ethane, it's an ethyl group. Imagine these stuck onto a larger chain off to the side, for example. Here's a propyl group. But to be specific, we would call this an N, that's an N, propyl group, because this has an isomer. This is a propyl group as well, since it has 3 carbons, 1, 2, 3. It has the same number of carbons and hydrogens as the N-propyl group. It's an isopropyl group. So far we have some good consistency in naming. That's not always going to be the case. Moving on to 4-carbon substituent, we're going to have 4 different isomers of butane as an alkyl group, as a butyl group. So we have an N-butyl group, an isobutyl group, a secondary or sec-butyl group, and a tertiary or tert-butyl group. So now we have some new words again. You can go crazy with terminology, but in this case it's pretty important. We need to back up just a tad. So when you refer to a carbon, like in the propyl group right here, this carbon has only one other carbon attached to it. Notice. That's a bond between two carbons. We would refer to this carbon as a primary carbon. Because it's attached to only one other carbon. Now, this is just going to be a logical progression. A carbon down here, for example, say in the butyl group, is a secondary carbon. Why? Because it is connected directly to two other carbons. So all you're doing when you say primary, secondary, or tertiary for a carbon is looking to how many carbons it's attached to. And this is not knowing really what's attached over here, okay? So we have to keep that out of this at this moment. Here is a tertiary carbon. Because this carbon right here is connected to 1, 2, 3 other carbons. So that's where you get the secondary butyl and the tert butyl groups. Whenever you stick one of these groups on another molecule, you refer to it as that group. So here's a couple of examples of naming. For example, I'm going to draw a hexane. 1, 2, 3, 4, 5, 6 carbons is a hexane. Linear alkane. Now, what if I put a group attached here where there's a carbon there, carbon there, carbon there, carbon there. We number our carbon chain 1, 2, 3, 4, 5, 6 from one end to the other, placing this substituent at the lowest possible number. So we wouldn't call this 5 position, we call it the 2 position, if that makes sense. So, and this group we see right above here, since we're able to quickly interpret line structures from more fully drawn out ones as a tert butyl group. So this is 2 tert butyl or T-butyl. Sometimes you see it, often you see it like that, hexane. 2 T-butyl hexane, 2 tert butyl hexane fully describes the structure of this molecule. Now, we're supposed to name compounds by finding the longest parent chain. So I proceeded here showing 1, 2, 3, 4, 5, 6 as the longest chain and the parent name of the compound, hexane. Is that absolutely correct? Because what if we look at a chain like this? 1, 2, 3, 4, 5, 6, 7. Well, look at that. I've discovered that in fact, this molecule has a longer chain than 6 carbons. It has a 7 carbon chain and really, more correctly, should be a heptane. So if it were a hexane, it would be 2 tert butyl hexane. As a heptane, it's 1 position, 2 position, 3 position, getting a little crowded, and then the rest of it is 4, 5, 6, 7. So at the 2 position, there are 2 methyl substituents. So it would be 2, 2 dimethyl, 2 methyls. And then at the 3 position, there's a methyl substituent. Look at that. And so it would be 3 methyl heptane. So the second name here is in fact a more correct name. Now, my earlier point of being able to unambiguously draw a structure from a name actually works for both of these. So, although it's incorrect, 2-T-butylhexane describes this molecule. If you're told to draw 2-T-butylhexane, you would draw this molecule. But according to the absolute naming rules, the more correct name of this is 2,2-dimethyl-3-methyl-heptane. And so, I urge you to read the sections described there. So on Canvas, the module reading assignments will be posted. There'll be, and also solutions to the book problems and so forth. So, Module 2.